would get pushed away. And you can see how the center of Susan's shirt there is being pushed out, gets stretched, right? If we increased that stretching, put a bigger lens in place, it would get to the point where not only is it stretched, but you could actually see light coming over the lens and under the lens. Yes?
Just want to give you a 10-minute warning.
Great. Okay. So you can see things coming over the lens and under the lens. And ultimately, you can get to cases where you have many multiple images. So here you can see Susan upright, and flipped over. Those are the kind of distortions that gravitational lenses can create. It's nice to see it in an image where you can recognize it. Okay? So I'm just going to skip over this and say that we now see many of these gravitational lenses. So let me show you what's happening here. This is a big galaxy in the center of a galaxy cluster. And you can see a bunch of arcs around it, right? Those arcs are actually galaxies that are actually sitting right here near the center, way behind that cluster. And their light comes toward the cluster and is bent around it till it comes toward us. So these giant arcs that occur are caused by gravitational lensing, and they let us measure the mass of the object that's doing the lensing. To show you the most extreme case, imagine for yourself what happens if an object is directly behind a gravitational lens. So light comes over the top and bends toward you, and light comes around the side and bends toward you, and light comes around the other side and bends toward you, right? It should go everywhere. So an object can turn into what? A ring. This is called an Einstein ring. And they really happen. That's the astounding thing about this. It's not just like an idea. You can look up in the sky and they're there, right? Amazing. So this is actually one blue galaxy that is directly behind us. And we're seeing its whole complicated structure stretched out into a ring all the way around this galaxy. The presence of this ring allows us to measure the mass of this object inside very accurately. And in a way that's completely different from measuring motion. And what does it show? It shows that there's an enormous amount of dark matter. Okay? So we got the hint from people like Zwicky and Vera Rubin that there was dark matter from those dynamical measurements in the middle of the 20th century. In the beginning of the 21st century, we used gravitational lensing to say, provide a completely independent check on this. And what we found is, it's true. There really is all this mass out there. Okay? So there's many more images of this. If you search strong lenses, you'll get to see lots of wonderful things. Remember that the Hubble Space Telescope took a lot of these images, but we're about to have the James Webb Space Telescope launched in just a few weeks. And it will allow us to make much more precise measures of these kinds of things. So I look forward to seeing many more of them in the near future. So why do we think there's dark matter? Two different ways of measuring the masses of galaxies. And they both show much more mass than the visible matter we see. And, another thing is, this invisible matter appears everywhere. Like there's no galaxies that don't have it. That's another way of kind of checking. Like if it really is this stuff, it should be all over the place, right? Like ordinary matter. And it is. Okay? Visible objects could not even form or hold together. Remember what I said about the coma cluster? If it was moving that fast, it would fly apart without this invisible matter to hold it together. The Milky Way would fly apart without invisible matter to hold it together. So we know it's really there. We see its effects. We don't see it. But we see its effects through its gravitational effects. The last thing I want to say is that this is often called dark matter. And this is kind of problematic for a long list of reasons. It isn't actually dark. Right? This stage is dark. It's actually invisible or transparent. Right? It isn't really the right thing to call it dark matter. So when I look at this picture, my wife's sitting looking at a Lake Michigan sunset. There's windows here. There's the air. Brought up the air as a transparent thing. It's really there. We don't call the air dark. Right? So it's really probably a mistake to call it dark matter. And we probably should speak about it as invisible matter. And this is one of those mistakes that has kind of consequences. it has meaning in the world that wasn't intended when the name was chosen. And if you want to think a little bit more about this and the meaning of choosing terminology like this, I would encourage you to consider reading Chandra Prescott Einstein's new book called The Disordered Cosmos. This is a really great book about the cosmos, about being a scientist, about dark matter, dark energy, space-time, but also about the ways in which science interacts with society and the ways in which names and choices that we make might influence how science can or will interact with society. So I just want to give a plug for this book. Chanda is a colleague. She's a brilliant young scientist, and I really hope that some of you will think about it. And I'll stop there. I can take a few questions if people have them, and I want to make sure you get to where you need to be.
That was our presentation. We should have some time for questions. I'll be taking them and then recommending them. We've technically got 3 minutes left. If you want to stay just a couple minutes late and be a little late to your fifth block, that's probably all right. I'm also going to have a follow-up meeting next week in Space Club to talk about this and some of our further questions and interests and stuff. All right, with that, I'll take away for questions. Start over there in the bush.
So we see dark matter mentioned a whole lot in sci-fi literature.
Yep.
And generally it seems to be some sort of substitute for like this extremely powerful weapon. Is dark matter a weapon?
No. As far as we know, whatever this dark matter is, physicists think it's probably some kind of particle, or maybe many particles, many kinds of particles, we don't know. But the only way they interact is through gravity, as far as we can tell. Now, if you have something that only tugs with gravity, and it's a particle, what are you going to do with it? Like, not much, unless you want to hold together a galaxy. It's really good for that. It's not much good for anything else. It doesn't stick to itself, even. So you can't, like, make a blob of it.
Is it a dark matter laser?
Sadly, no. I mean, you can in your story. That is a great thing about stories, but they're just not real.
How come dark matter has never been observed or has never been a factor in calculating stuff within our within our solar system?
It's a great question. So there is dark matter in our solar system. The local density of dark matter is much lower than the local density of ordinary matter. That's because of the sun. Ordinary matter, because it emits light, and I know this explanation is going to be brief, so it's not going to really give you the whole story. But because it can emit light, it can lose energy and collapse together to form incredibly dense objects, like the sun. So right here, the sun is the dominant mass, even though there's dark matter spread throughout the solar system, pretty uniformly throughout the solar system. So the sun is the local thing that yanks stuff around. If you look on larger scales, though, the stars in the Milky Way make up a very small part of its mass. Right? But if you get close to one, then they tug on you really much. So that's basically
Are there any ideas of how we might be able to observe dark matter?
Absolutely. Most of there's two ways. One is the astrophysical way, which you've seen what we've been doing. And it's told us, it's really out there, it's really in all these places, so we've used that method to tell that it's there. We'd also like to see it like right here in the lab. And the way physicists detect particles in the lab is to look for them to interact with other particles, and to do that inside detectors where they can measure that interaction. So particle physicists build giant detectors and put them deep underground, for example, and they just sit there and wait for one of these particles to pass through, and they hope that it will have an interaction that will let it bump into an atom, and we'll get to see that atom move, and then we'll say, a dark matter particle just came in and did this. We've been working on that, though, for about 60 years. The detectors started very small and insensitive. They got bigger and bigger and bigger. They're still getting bigger. Because if the interaction is really rare, you need a big detector to see it. I would say that there was great enthusiasm for this when I was young, and that enthusiasm is beginning to fade. Because, people put their whole careers into trying watching these empty containers and waiting for something to happen. Not at all.
How big exactly are these?
Well, the biggest ones are much bigger than this theater, maybe 80 meters across, buried deep underground, filled with substances like liquid argon. And there's reasons why the liquid argon. It could be almost any matter, but what we get out of things like liquid argon are great purity so that you can tell only the dark matter particle.
All right, Jasmine, then Nick, then Owen, and then I think we have to go. I'm sorry.
Okay.
I'm just curious, like, how do these scientists, like, derive the equations, and how do they know that it would be useful for them to, like, make these equations to measure all this stuff?
Like these gravitational ones?
Yeah.
So Newton and Einstein were both motivated by understanding what they could see. So for Newton, it was the solar system. There are these amazing patterns of motion in the solar system. And at the time of Newton, no one knew why they were that way. And he wrote down one equation from which all of the things we saw could be derived. And that convinced him that this equation had some truth to it. Right? What Einstein did was to reconsider Newton's gravity because Newton's gravity, it turns out, wasn't quite right. It was very close to right. But there were tiny things, even in the solar system, like the precession of Mercury, that weren't right. And no one could figure out why. And so Einstein rethought gravity, came with this completely different theory of gravity. And then he said, what would the equations mean? They mean things like bending of light. Look, it actually happens.
Nick?
Okay, so since dark matter has this like intense gravitational pull, what would happen if like a rocket like came in contact with it?
Yeah, no rocket cannot come in contact with dark matter. Dark matter is everywhere in the galaxy, it's everywhere in the cosmos, it's concentrated around galaxies. Dark matter is here in this room, it's passing through you right now. You're embedded in it. Why doesn't it bother you? Remember, it doesn't interact. Remember what I said about an invisible object? It really doesn't interact. It doesn't interact. Like it can pass right through something. There are other things that do pass through you, like radio waves. I can stand here, the radio waves go, you can't put the radio behind me and have them just stop, right? So it's here. It's not a thing you run into.
Quick clarifying thing for that, and correct me if I'm wrong. I think the thing with dark matter is not necessarily that it has a more intense gravitational pull than ordinary matter. It's just that that same gravitational pull is something that we can't see because it's invisible. So it's stranger, but it wouldn't be different than coming into contact with ordinary matter that has a gravitational pull. Am I correct about that?
It's quite true. The reason we're pulled toward the Earth is that all the Earth is down there. The dark matter is here, 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 it's everywhere. So you get pulled in every direction by the dark matter of the present, instead of just down.
How quick is your question?
Really quick, it's on the detector.
Okay.
So that sounds a lot like a neutrino detector. Do you get like cross-contamination where you, how do you set it up?
Yeah, that happens. There are lots of things that might interact with your detector, and you have to know about all of them and eliminate everything else instead of something else. Super hard. Well, that's part of how we learned how to build such detectors. We knew there were other things to detect that were good to detect. And then we started.
I'm so sorry to cut you off, but we're 5 minutes into our fifth block. Can everyone give a round of applause for our